Welcome to another deep dive. Today we're zeroing in on large language models, LLMs, and a really innovative breakthrough that's making them smarter and, well, remarkably more efficient. If you've ever wondered how these powerful models are learning to think with greater depth, this deep dive is definitely for you.
Yeah, we're exploring a fascinating stack of research today. It's titled Test Time Scaling with Reflective Generative Models, and it introduces this new model called Metastone S1. Our mission, really, is to uncover how Metastone S1 gets these impressive reasoning capabilities, even rivaling some huge models, by cleverly refining its own thought processes, but without needing massive amounts of new data.
Okay, so let's set the stage a bit. We've seen incredible advancements in LLMs recently. Models like OpenAI's GPT-4, Google's Gemini, they're pushing boundaries. But here's where it gets really interesting, according to the sources. Some of their most advanced reasoning, like what we see in OpenAI's O3 model, isn't just about the model's size or initial training. It seems to be significantly influenced by something called test time scaling, or TTS.
hmm And what's particularly insightful there is how O3 uses TTS. The research shows it can generate, believe it or not, up to 124 different candidate solutions for just one query, and then it critically evaluates and searches through multiple reasoning paths. That's a profound shift from older models that just give you one shot, one output. It lets the model dynamically adapt, deepen its approach to new tasks.
That sounds like a really powerful capability. And the sources, they categorize TTS into two main types, right? Internal and external. What's the key difference
That's
there?
right. Internal TTS involves strategies like chain of thought, COS. It essentially extends the model's thinking aloud process. Now, that's useful, but it can sometimes lead to what's called false positive reasoning. Basically, a flawed thought process might, just by chance, still get the right final answer during training. External TTS, on the other hand, focuses on a different problem. How do you select the best reasoning process from several options? And this approach, well, it's consistently proven more effective for boosting performance. Often uses something called a process reward model, a PRM, to pick out the high-quality reasoning paths. Methods like best-of-n sampling or beam search fall into this category.
And there's an important detail the research points out. The best external TTS approach might actually depend on the LLM's size, its parameter count. It suggests that if a model is under, say, 32 billion parameters, search methods like beam search tend to work better. But for the bigger models, 32 billion parameters or more, sampling methods like best of n seem to take the lead.
Which brings us to a really fundamental challenge. How can we actually harness the power of these advanced TTS techniques, especially external TTS, but more efficiently? Current process reward models, the PRMs, they often hit roadblocks. They frequently demand a whole new large-scale LLM just for training them. That means substantial computational costs.
Right, building another huge model just to supervise the first one.
And on top of that, they typically rely on process-level annotations. That means humans have to painstakingly label every single step of an AI's reasoning, which is, as you can imagine, incredibly expensive and time-consuming to get.
So those are the hurdles. And this is where this new idea, the reflective generative form in Metastone S1, comes in. Sounds like it's offering a novel solution designed specifically to select those high-quality reasoning trajectories, but while dodging those computation and annotation problems.
It is. The core innovation of this reflective generative form is quite clever. It shares the fundamental brain, the backbone of the policy model, that's the LLM generating the answer, and the process reward model within a single network.
One network doing both jobs.
One network. This means the same model can both predict reasoning paths and then select the best one, all in a unified interface. And the critical breakthrough here is it gets rid of the need for that expensive process-level annotation. It introduces a self-supervised process reward model, or SPRM. This SPRM learns purely from outcome rewards. It just needs to know if the final answer was right or wrong. That's it.
Wow, okay. So it doesn't need someone grading every step of its homework, just the final grade.
So it's sort of like that, yes. It learns to figure out the good process just by seeing the final result.
That really does sound like a shift. What are the main contributions the researchers are highlighting with this new form?
Well, first, they propose a clear definition of this reflective generative form, which is key because it enables that single network to do both prediction and selection without the process labels. They also provide some really comprehensive analysis on something they call the aha moment. We should definitely get into that later, plus insights into scaling laws and the model's robustness. And, of course, the pretty impressive state-of-the-art performance that Metastone S1 actually achieves.
Okay, so given it's this single unified network, how does Metastone S1 actually manage to generate and score its own reasoning? What's happening inside?
So that unified interface lets the policy model part generate multiple possible thinking processes. These are marked internally with specific tokens, kind of like think and think tags. Then the SBRM part, which shares the same backbone but has an added, very lightweight component, like a small extra head steps in, to evaluate each of those generated thinking processes.
And how does it evaluate them? Does it look at the whole thinking process all at once?
No, it's more granular than that. First, it breaks down the reasoning trajectory into distinct steps, using existing structural markers in the output, like good place. Then, for each individual step, it predicts a score. It captures the context by using the model's own internal hidden representations, specifically from the second to last layer. The final score for a whole reasoning path is then calculated by combining these step scores, using the geometric mean.
Okay, so the policy model and the SPRM, sharing that backbone, means they get trained together, they kind of refine each other.
That's the idea. It allows for joint end-to-end training. And for optimizing that SPRM hedge ability to judge, they introduced what they call the self-supervised process reward loss, or SPR loss. This is really crucial because it lets the model learn to discriminate good process from bad, using only the outcome reward, just whether the final answer was correct.
How does it handle cases where maybe the final answer is right, but the reasoning was flawed? That seems like it could confuse the model.
That's a great point. They use a dynamic weighting system specifically for that. It helps mitigate that noise you mentioned when a correct answer might pop out from incorrect steps. This system helps the SPRM progressively learn to evaluate the process better by basically enlarging the score gap between correct and incorrect reasoning steps over time.
Makes sense. And then at inference time, when you actually want an answer from Metastone S1, how does it all come together?
It's a pretty clear three-step process then. First, the policy model samples multiple potential thinking processes. Let's say generate a few different ways to solve the problem. Second, the SPRM evaluates each of these generated processes, assigns that final score to each one. Third, the reasoning trajectory with the highest score gets chosen. And that selected, high-quality path then guides the policy model to generate the final answer. The model also allows for controllable thinking length. It has these reasoning effort modes, low, medium, and high, sampling 2, 8, or 32 trajectories, respectively.
Right, so you can dial up or down the effort it puts in. Okay, now for the results. The proof, as they say. What did the experiments show about Metastone S1's actual capabilities?
So the researchers tested Metastone S1 at 3 different sizes, 1.5 billion, 7 billion, and 32 billion parameters. And it's really important to note the SPRM component only added a tiny number of extra parameters, 5 million, 26 million, and 53 million, respectively. Very small overhead.
Tiny compared to the base model size.
They trained these on a dataset of 40,000 high-quality math examples. Then they evaluated them on standard benchmarks covering math reasoning like AMY24 and AMY25, coding with Live Code Bench, and Chinese reasoning with CEVAL. They used the pass at one metric.
And the findings, did this reflective generative form actually deliver?
Yes, it seems so. The reflective generative form consistently boosted the baseline performance across all the model scales they tested. It was particularly strong in mathematical reasoning. For example, Metastone S1 got performance gains of up to 18.6 points on AME24 compared to its own baseline without the reflective part. And when they compared it to other models out there, Metastone S1 1.5b and 7D consistently outperformed other open source models of comparable or even larger sizes. Get this, the Metastone S1 1.5b in its high effort mode even surpassed some 7B and 8B parameter models on AME24.
Wow, so a smaller model punching well above its weight. How did the big one, the 32 billion parameter version, fare against a really top-tier models?
At that 32B scale, Metastone S1 High achieved really superior results on the math reasoning tasks. It outperformed all the listed open source models of comparable or even larger size. We're talking a 4.4% gain on AME24 and 3.6% on AME25 compared to the closest competitors they listed. And crucially, its performance was comparable to OpenAI's O3 mini series.
Okay, comparable to O3 Mini. That's a strong claim.
Well, the numbers they report show, for instance, on AME24, Metastone S132B High scored 85.2% compared to OpenAI O3 Mini's 79.6%. On AME25, it was closer to 73.6% versus 74.8%. So it highlights its strong competitiveness, particularly in math, but also more generally.
Now, you mentioned something earlier that sounded really intriguing. The aha moment. What exactly is that referring to in this research?
Right, the aha moment. It refers to this really distinct point they observed during training where the model's ability to tell the difference between correct and incorrect reasoning paths just suddenly improves quite sharply. So Initially, the model, it seems it really can't tell the difference. The scores for good and bad reasoning steps were kind of jumbled. But after a certain number of training steps, they found it was around 10 to 50 steps. Depending on the model size, the optimization trends for the correct and incorrect paths clearly diverge. They split apart.
So like a switch flips.
It suggests the model has genuinely begun to correctly judge the quality of the reasoning content. They show an example where an incorrect step was scored, say, 0.52 before this moment, and then it dropped way down to 0.12 after. It's like the model suddenly gets it, figures out what good reasoning actually looks like internally.
That's a fascinating insight into how it learns. What about scaling? Did they look at how performance changes with more computation?
They did. They observed a clear positive correlation between the final performance and the logarithm of the computation budget, which basically indicates that performance can be enhanced by exponentially scaling either the number of parameters or the reasoning length, how many trajectories it samples. Although they did note that the performance improvements start to slow down quite a bit after scaling the reasoning length beyond 32 times the baseline, diminishing returns eventually.
Okay. And the ablation studies,
Yeah.
where they take parts away to see what matters most. What did those reveal?
Those studies really confirmed how effective both the SPRM and that self-supervised optimization method, the SPR loss, were. Despite having so few extra parameters, the SPRM actually outperformed much larger, traditionally trained reward models. They specifically compared it to 72 billion parameter ORM and PRM models.
So the smaller self-supervised component did better.
According to their results, yes. It also showed strong zero-shot generalization, meaning it could effectively identify logical errors and calculation mistakes in new areas, like coding problems, even though it wasn't specifically fine-tuned on coding process example.
Impressive adaptability.
And furthermore, their SPR loss method, the self-supervised optimization, achieved better performance and showed a significantly larger score gap between correct and incorrect solutions compared to more standard loss functions that just use the final answer correctness. This really highlights how their method effectively reduces the impact of those potentially noisy labels, the right answer for the wrong reason problem.
So wrapping this up, what does this deep dive really show us? It seems clear that Metastone S1, using this novel reflective generative form, is a big step. It lets a single LLM both generate and intelligently select high-quality reasoning paths. And it gets performance comparable to heavy hitters, like OpenAI's O3 Mini, but with significantly fewer parameters, directly tackling those big challenges of compute cost and data annotation.
I think this work really demonstrates the power you can get from unified interfaces and self-supervised learning when it comes to enhancing LM reasoning. It's quite elegant. And those insights from the aha moment analysis and the scaling laws, they further underscore just how effective this whole approach seems to be.
It certainly leaves you thinking about how these models can genuinely learn to discern, to refine their own internal thought processes. What's the one thing that really stands out to you from all this?
For me, it's the idea that a model can learn to tell good reasoning from bad, not by being explicitly told every step, this was right, this was wrong, but just by observing the final outcome. Did it get the answer right or not? That approach, learning process quality from outcome alone, really points towards a future where LLMs might become much more autonomously discerning, more self-correcting in how they solve complex problems.